Here's the last part of the grade 12 advanced functions exam review. I'm going to go through this section quickly: logarithmic functions, rational functions, and inequalities. So let's start with log functions. So you need to know how to convert from exponential form to logarithmic form and vice versa. So if we have an exponential expression, 5 to the 4 equals 65, I could rewrite this in logarithmic form by writing log base 5 of 625 equals 4. So a logarithmic expression is going to have the same base as the base of the power, and the answer to the logarithmic expression is always an exponent, so it's the exponent of the power, and 625 is what we call the argument of the logarithmic expression. Let's go the other way. If we have a logarithmic expression, we want to convert it to exponential form. Well, the base of the log is equal to the base of the power. The log is equal to, the answer to a log is always an exponent, right? So the exponent on this power is going to be the answer to the log, so 4. And this is equal to our argument, so 5 to the 4 equals x. Now let's use our understanding of logs to actually evaluate a logarithmic expression. So log base 4 of 64, what that means is, it means 4 to the power of what equals 64. So we want to figure out what power do we raise the base of our log to get the argument 64. So the easiest way to think of this is, can you rewrite 64 as a base 4 power? Well, 4 cubed is 64. So I can replace 64 with 4 cubed. So now what this says is, it means 4 to the power of what equals 4 to the power of 3. Well, 4 to the 3 equals 4 to the 3. So our answer is 3. The answer to a log is the exponent that we raise the base to get the argument. 4 cubed is 64, so the answer to this expression is 3. Let's solve some exponential equations now. So I have 4 to the 2x plus 5 equals 32 to the 4 minus x. So if you have power equals power, you should try and write those powers with the same base, because if you can, it makes solving it very easy. So 4 is a 2 squared. So I'm going to rewrite 4 as 2 squared. And 32 is a 2 to the power of 5. So I'm going to rewrite that as 2 to the power of 5. Then I'm going to use my power of a power rule, multiply the exponents. So I've got 2 to the 4x plus 10, right? Do 2 times 2x plus 5 is equal to 2 to the 20 minus 5x. 20 minus 5x. So I've got powers of 2 equal to each other. That means the exponents have to be equal to each other. So that means that 4x plus 10 has to equal 20 minus 5x. And then what we can do from here is we can just solve for x, right? We have a linear equation that we can solve. So we'll have 9x equals 10, right? Add the 5 over, subtract the 10, x equals 10 over 9. So, and whenever you are doing solving an equation, don't forget you can check your answer, plug 10 over 9 back into the original equation, and you have your answer. Okay, let's look at a more difficult one where we can't necessarily write these powers with the same base, or we could, but it would be very difficult. So since we can't rewrite 4 and 7, we can't rewrite those powers with the same base, what we're going to have to do is find a way to get our unknown out of the exponent. So when your unknown's in the exponent, you can get it out of the exponent by using the power rule of logarithms. So take the log of both sides, right? We can do whatever we want as long as we do it to both sides. So we'll do log of 4 to the 2x minus 5 equals log of 7 to the x. And then the power rule of logs tells us we're then allowed to rewrite the exponent of the argument as the coefficient of the log. So I've got 2x minus 5 log 4 equals x log 7. And now whenever you're solving equations, actually let me expand first. So I'm now going to expand this expression. So I'll do 2x times log 4 and negative 5 times log 4. So 2x log 4 minus 5 log 4 equals x log 7. So whenever you're solving equations, our goal is to isolate x. So we're first going to want to bring all the terms with x to one side. So I have two terms with x, this one and this one. So I'll bring those both to the left, and I'll take my term without an x to the right. So 2x log 4 minus x log 7 equals 5 log 4. Now both terms on the left have an x, so I'm going to common factor it out. So x, take it out, divide both of these by x, and I get 2 log 4 minus log 7 equals 5 log 4. Now I can isolate the x just by dividing what it's being multiplied by to the other side. So x equals 5 log 4 over 2 log 4 minus log 7. And then you can just evaluate this on your calculator. If you're going to type it in one step, just make sure you put the denominator in brackets so your calculator knows to divide by the difference of those two. And we'll get an approximate answer if we evaluate this of about 8.385. So that's solving two different exponential equations. Let's look at one that has e. So once again, our unknown is in the exponents. We're going to want to take the log of both sides. But instead of taking the log where the base is 10 of both sides, it's actually going to help if we take a log base e of both sides, which is the natural logarithm ln. So I would take the ln of both sides. I would take ln of e to the x equals ln of 5. And you'll see soon why I did that. So now we can bring the x down. We have ln e equals ln 5. Well, ln is a log base e. So this means e to the what equals e? Well, e to the 1 equals e. So this is just, ln e is just 1. So x times 1 is x. So x equals ln 5. And I can just type that on my calculator, ln 5, and I get about 1.61. X is about 1.61. And you can check this on your calculator. E to this should equal about 5 because we've done some rounding. Now let's solve some logarithmic equations. So you're going to have to remember your log rules here. So first mistake, do not expand into here. Do not do this, right? This doesn't mean log times this. It's log of this. It's just the argument of the log. So don't do that. What we're going to want to do is we're going to want to bring all the expressions with a variable to one side. So I'm going to leave the log base 5 of 2x plus 1 on the left, and I'm going to bring over the other log base 5 of x plus 2, and I'll leave the 1 on the right side of the equal sign. Now when you have two logs with the same base, this is important, they have the same base. When you have two logs with the same base being added, this is equal to, you can write it as one log with those arguments being multiplied together. It's equal to log base 5 of the product of the two arguments. And you can only do this when the bases are the same. So this is equal to log base 5, and then the product of this would be 2x squared plus 4x plus 1x, that's plus 5x, plus 2 equals 1. Now once you get to this step, once you have a log equals a number, you're going to convert it to exponential form. So 5 to the power of 1 equals 2x squared plus 5x plus 2. And now we just have a quadratic we have to solve. 5 to the 1 is 5. Bring it over. 0 equals 2x squared plus 5x minus 3. And to solve this, I'm just going to quickly use the x shortcut. Product of a times c, that's negative 6. Sum of b, that's 5. So the numbers that work for this are 6 and negative 1. Divide them both by 2. Reduce this to 3 over 1. And my factors are 1x plus 3. And once again, you could factor by grouping here. I'm just using a shortcut. And the other factor is 2x minus 1. Set both of those to 0 and solve. If I set this to 0, I'll get x equals negative 3. Set this to 0, I get x equals a half. Now whenever you solve an equation that has a logarithmic expression in its equation, you have to check and make sure that you don't have what's called an extraneous root. Did our solving process come up with an answer that doesn't actually work in the original equation? So what we have to check and make sure is that neither of these values make any of the arguments in the original equation equal to a negative number, because we can't take the log of a negative number. So a half. Does a half work? So we'd have 2 times a half plus 1. That's just 2. So we can take the log of 2. That's fine. And here we'll just have the log of 2.5. That's fine. Both of the arguments stay positive when x is a half. But if x is negative 3, it actually makes both of these arguments negative, which we can't do. We can't. Logarithmic expressions are undefined for negative arguments. So negative 3 we actually have to reject and say that's an extraneous root, but a half we can accept. Let's do one more logarithmic equation, and this one's actually a little quicker. So we have log base 4 of x equals, now I have the difference of two logs with the same base. So when we have the sum of two logs with the same base, we can multiply the arguments. When we have the difference of two logs with the same base, we can actually divide the arguments. So we can write it as 1 log with the arguments divided. 15 divided by 3 is 5. So what I have now is a log base 4 equal to another log base 4. So just like when we had two powers with the same base equal to each other, we could just write the exponents equal to each other. When we have two logs with the same base equal to each other, we can just write the arguments equal to each other. So logically, the only thing that would make these two sides of the equation equal is if this x was a 5. So x equals 5. That one's done. Let's do reciprocal functions very quickly. So I just want to know what the graph of 1 over x squared minus 4 looks like. So often it helps to understand what x squared minus 4 looks like. So x squared minus 4, let's just get some properties of this down. So x squared minus 4, no, that's in factored form. It's a difference of squares, x minus 2, x plus 2. So it's got x-intercepts at negative 2 and 2. The vertex has to be between negative 2 and 2, which is at 0. If I plug 0 into here, I would get 0 minus 4, which is negative 4. So the vertex is at 0, negative 4. So this function, I already have a general idea of what the denominator would look like if I was just graphing the denominator. Let me just quickly make a table of values for this. For x squared minus 4, so the vertex is at 0, so I'll put that in the middle, and I'll pick some points on either side that include the x-intercepts. And then if I were to figure out y for x, the y values for x squared minus 4, if I were to plug them in, I already know this point, and I know these are both the zeros. So negative 1, if I plugged it in, I would get negative 3, which means the same thing for 1. And then 3, if I plugged it in, I would get 5, which means the same thing for here. So I have some points I can plot here. So 1, negative 3, negative 3, negative 3 was up at 5, 5, 5. So here's what x squared minus 4 looks like. Now, this isn't what I wanted to graph, right? I want to graph the reciprocal of it. So I'm now going to use these points to get points on the reciprocal. So for x squared minus 4, I want to make a table by, since my function I want is 1 over x squared minus 4, I can get the y values by just doing 1 over the y values of x squared minus 4. So you keep all the same x's, and then you just do the reciprocal of all the y's. So 1 over 5, that's 0.2. 1 over 0, that's undefined. And when you have an undefined value in your function, that tells you that's where a vertical asymptote is going to be, right? The zeros of the denominator are going to give you where the function is undefined. So find the zeros of your original function in the denominator, and those are where your vertical asymptotes are going to be. 1 over negative 3, negative 0.3, negative 0.25, negative 0.3, undefined, and lastly 0.2 again. So at 3 I'm at 0.2, which is about here. Negative 3 I'm at 0.2. 0 I'm at negative 0.25. And I have points here and here as well. These are just all approximate. And then I have to understand some properties of reciprocal functions. So when the function in the denominator is decreasing, the reciprocal function is going to be increasing. Oh, and I should have also reminded you, reciprocal functions always have a horizontal asymptote at y equals 0. Right? The bigger and bigger and bigger you make the denominator of your function, the closer and closer and closer the function is going to get to 0, but it's never going to get there. So the denominator function is increasing, which means the reciprocal is decreasing. So I get these two branches. Right? They have opposite intervals of increasing and decreasing. Blue is decreasing, red is increasing. Blue is increasing, red is decreasing. And then let's get the points in between the vertical asymptotes. So I have those points, and so for these points, to the left of the y-axis, the blue function is decreasing, which means the red one is going to be increasing. And then to the right, the blue one is increasing, which means red is going to be decreasing. So the red function is the reciprocal function that I wanted to graph. So that's how you graph the reciprocal of a quadratic. Graph the quadratic, then get points for the reciprocal function by keeping the x values and then doing the reciprocals of the y values. Let's do the quotient of two linear functions. So if we want the quotient of two linear functions, let's just get where our asymptotes are going to be and where the x and y intercepts are going to be, and then you're going to see the general hyperbola shape that it's going to form. So let's get our vertical and horizontal asymptote for this function. So vertical asymptote, that's where the function's undefined, so we look at the 0 of the denominator. 0 of the denominator would be negative 1, so there's a vertical asymptote at negative 1. So I could plot that right now, vertical asymptote at negative 1. Horizontal asymptote is actually going to be equal to the quotient of the leading coefficients of the numerator divided by the leading coefficient of the denominator. So 2 divided by 1 is 2, so we're going to have a horizontal asymptote at y equals 2. So I can plot that now as well. Whenever you have one vertical and one horizontal asymptote, it's going to form a hyperbola shape. So we just need to know that, all we really need to know is what one of the branches looks like, and we know hyperbolas are symmetrical across this point of intersection here, and we could use that property to graph the other branch. So let's just get a couple other key points. So let's get an x-intercept and a y-intercept. X-intercept. So if we want the x-intercept, we would set y to 0 and solve. So to make this equal to 0, all we have to worry about is what would make the numerator be 0. So 0 equals 2x minus 3. Solve this. We get 3 over 2, which is 1.5. So the x-intercept is at 1.50. So 1.5 is here. There's the x-intercept. And notice, in relation to the point of intersection here, it is 1, 2.5 to the right, 2 down. So I can go 1, 2.5 to the left, 2 up, and there's a point on the other branch of the hyperbola. Let's now find the y-intercept. Y-intercept, you just set x to 0, so let's just evaluate h at 0. H at 0 would be 2 times 0 minus 3, which is just negative 3, over 0 plus 1, which is 1. So h at 0 equals negative 3, so my y-intercept is at 0, negative 3. 1, 2, 3. There's a point on this branch of the hyperbola. Let's find a point on the other branch. So it's 1 to the right, 1, 2, 3, 4, 5 down. So I go 1 to the left, 1, 2, 3, 4, 5 up. Now let's just get one other point, just so we can see the curved shape of these branches of the hyperbola. So I'm just going to calculate one more point, maybe calculate either h at 1 or h at 2. So I'm going to calculate h at 1 just to get one other point, h at 1. So h at 1 would be 2 minus 3, that's negative 1 over 2. Be negative 1 over 2, so the point 1, negative 0.5 is on the graph. 1, negative 0.5. So that's 1, 2 right, 2.5 down. So I go 2 left, 2.5 up. So what this is going to look like, and I could get some more points, but what this is going to look like, here are the branches of my hyperbola. They're going to be approaching the asymptotes but never touch. So that's what my quotient of the two linear functions roughly looks like. The last question that we're going to do for this entire exam review is solve this rational inequality. So when solving a rational inequality, do not cross multiply, because that brings up a lot of problems with whether we're going to have to flip the inequality sign or not. So what you want to do is avoid multiplying both sides of the inequality. So what we want to do is move everything to the left. So I'm going to go through this relatively quickly. So leave the first fraction, bring over this entire fraction to the other side. So minus 2x plus 7 over x minus 3. And we want to know when this is greater than 0 now, because there's nothing left on the right. So what we're going to do is we're going to combine these two by getting a common denominator. So multiply this one top and bottom by x minus 3. So x minus 3 times 2x minus 3. Minus, multiply this one top and bottom by x plus 5. So x plus 5, 2x plus 7. All over the common denominator we've created, which is the product of our two denominators, x plus 5, x minus 3. So we want to try and get this into as much a factored form as we can. So let's expand the numerator and then see if we can collect and simplify this and factor. So if we expand the numerator, 2x squared minus 3x, 2x squared, so we'd have minus 3x minus 6x, that's minus 9x, plus 9, minus 2x squared plus 7x plus 10x, that's plus 17x, plus 35. All over. Our denominator is already fully factored, so I'm going to leave that. And then if I expand and collect the numerator, I've got 2x squared minus 2x squared, that's 0x squared, so those are gone. I've got negative 9x minus 17x, that's negative 26x. And I've got 9 minus 35, that's negative 26, over my denominator. And I'm just going to common factor my numerator, take out a negative 26, divide them both by negative 26, I get x plus 1. Okay, now the numerator and denominator are both fully factored. So in order to figure out when this is greater than 0, all I have to figure out is when I'm going to get a positive answer here. So what you can do is you can make yourself a factor table and test values within the intervals where you think it might change signs. So where would a rational function change signs? So it could change signs at an x-intercept or if it crosses a vertical asymptote. So let's write down where the x-intercepts are. So the x-intercepts are the zeros of the numerator. The only way the numerator could be 0 is if x was negative 1. And the vertical asymptotes are at the restrictions of the function. So what can't x be? What would make the denominator 0? Well, x can't be negative 5 or 3. So these are the three places where the function could change from being negative to positive. So I'm going to write them in order: negative 5, negative 1, 3. And I'm going to choose values within each of these intervals, and I'm going to list each of my factors and figure out the sign of each factor within each interval, and then therefore know the overall sign of my function. So my factors are, don't forget the negative 26, x plus 1, x plus 5, x minus 3. And then choose values within each interval, so negative 6, negative 2, 0, 4. And then all we're going to be doing is we're going to actually be testing the values, testing each of these values within each factor and get the overall sign of each factor. So negative 26 is always negative. If I plug negative 6 into each of these factors, I get negative here, negative there. So if I have any value less than negative 5 in this function, I'll get a negative times a negative divided by a negative times a negative. Even number of negative results in a positive overall value. If I plugged in negative 2, I would get negative, negative, positive, negative. Odd number of negatives, overall negative value. If I plugged in 0, positive, positive, negative, even number of negatives, positive overall value. If I plugged in 4, positive, 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 one negative number, so overall negative. So when is the function greater than 0? It's whenever it's above the x-axis. So it's greater than 0 here and here. So my solution to this inequality would just be the intervals that I see at the top of my factor table for where the overall sign of my rational expression is positive. So when it's less than negative 5, so when x is less than negative 5, or when it's between negative 1 and 3. Alright, that's the whole advanced functions course. Good luck on your exam.